Greetings. Today, we will explore the fascinating world of the traveling salesman problem, or the more commonly known as TSP. This problem involves finding the shortest route that visits a series of cities exactly once and returns to the starting point. While its premise is straightforward, the traveling salesman problem is a classic example of an NP-hard problem. As the number of cities increase, the problem becomes computationally intractable for exact methods with no known polynomial time algorithm guaranteed to solve all instances. In practical terms, solving the traveling salesman problem for large instances requires significant computational effort, and the problem is central to the study of optimization and complexity theory. Before moving forward, we would like to give you the historical background behind this problem. The origins of the traveling salesman problem can be traced back to the 19th century, with initial contributions by mathematicians like W.R. Hamilton and Thomas Kirkman. However, the problem gained significant attention in the mid 20th century with advances in the linear programming by George Dancy, Ray Fulkerson, and Selmer Johnson. Their work laid the groundwork for developing various algorithms and heuristics to tackle the traveling salesman problem. Now, moving on, we'll try to define the problem more mathematically using graph theory. We have also provided with an example in the slide. Mathematically, the traveling salesman problem can be represented using a distance matrix, where each entry denotes the distance between a pair of cities. The goal is to find a permutation of the city that minimizes the total travel distance. For example, given cities A, B, C, and D, the task is to determine the optimal route that minimizes the travel distance. Now, let's move on to graph theory terms. The traveling salesman problem can be represented as a graph G where nodes represent cities and edges represents routes between them. We define a binary variable xij that indicates whether a specific route is included in the tour or not. This formulation allows us to use various algorithmic approaches to find the optimal solution. Now, we will move on to the literature review part of our research. In our literature review, we analyzed various algorithms used to solve the traveling salesman problem. These included exact algorithms like the held carp and branch and bound algorithm, and it also included heuristic algorithms like the ant colony optimization, simulated annealing, and genetic algorithms. Each of these approaches offers a unique advantage and limitations in solving the traveling salesman problem. Now we'll be analyzing each of the algorithms one by one. Let's start by the exact algorithms. We'll first analyze the held carp algorithm. The held carp algorithm is a dynamic programming approach to solving the traveling salesman problem. Exactly. It is considered one of the most well known algorithms because it systematically explores all possible routes while avoiding redundant calculations. The algorithm relies on the principle of optimal substructure, meaning that optimal solution to the overall problem can be built from the optimal solutions to its subproblems. To do this, it uses memorization, where intermediate results are stored and reused instead of recalculated. To understand with the help of an example. Suppose you have four cities A, B, C, and D, and you need to calculate the shortest path visiting all cities. The algorithm starts by calculating the shortest path to the subset of these cities. For instance, it determines the cost of traveling from city A to subsets like BC or CD. It then combines these more minor results into more extensive solutions by incrementally adding cities to the tour. Held carp uses a recursive formula that calculates the minimum cost of reaching a city via all possible subsets of other cities. This formula ensures that no route is missed and every possibility is considered. Finally, after exploring all subsets, it reconstructs the optimal route by backtracking through the stored results. The held carp algorithm provides the exact solution, but it has a time complexity of big O of n square into 2 to the power n, where n is the number of cities. This exponential growth means that it becomes computationally infeasible for larger instances, but it is good as a gold standard for smaller problems. Now we'll come to another exact algorithm called the branch and bound algorithm. The branch and bound algorithm is another exact method for solving the traveling salesman problem, but it takes an entirely different approach than held carp. Rather than exhaustively evaluating every possible solution, it strategically eliminates large portions of the search space to save computational time. Here's how it works. The algorithm views all possible solutions as decision tree. The tree's root represents the starting city and each branch represents a potential path to another city. At each tree level, the algorithm branches out further by adding more cities to the tour. To avoid exploring every branch, it calculates a lower bound for each partial solution. The lower bound estimates the minimum cost required to complete the tour based on the current choices. For instance, if the current partial tour has already exceeded the cost of a known solution, there's no point in exploring it further. This process is called pruning, as it effectively cuts off unpromising branches. Branch and bound combines systematic exploring with these intelligent pruning techniques, allowing it to find the optimal solution without evaluating every possibility. While it is highly efficient for small and medium sized problems, its worst case time complexity is also exponential, making it impractical for very large instances. Now we'll move on to the heuristic methods of solving the traveling salesman problem. The first heuristic algorithm that we will be looking at is the ant colony optimization. It is a heuristic algorithm inspired by the foraging behavior of real ants. When ants search for food, they lay down a chemical substance called as a pheromone on their paths. Other ants are more likely to follow paths with higher pheromone concentration, but they also explore new routes. Over time, shorter and more efficient paths accumulate more pheromone, reinforcing their use. In the context of traveling salesman problem, virtual ants are used to simulate this behavior. Each ant starts at a random city and constructs a complete tour by visiting all cities exactly once. The decision making process of the ants involves two factors. The first one being the pheromone levels. Paths with higher pheromone levels are more attractive to ants. This reflects the collective memory of the colony, guiding ants towards promising routes. The second is the heuristic information. This measures how desirable a path is based on the distance between cities. Shorter paths are more likely to be chosen. The probability of an ant choosing a specific city depends on a formula that balances these two factors. After all ants complete their tour, the pheromone levels are updated. Shorter routes receive a higher pheromone reinforcement, while all paths experience pheromone evaporation to prevent premature convergence to a suboptimal solution. Ant colony optimization has several parameters that can be fine tuned, such as the rate of pheromone evaporation, the number of ants, and the balance between exploration and exploitation. The algorithm repeats this process over many iterations, gradually converging towards high quality solutions. One of the strengths of the ant colony optimization is its ability to explore a vast solution space while avoiding local optima efficiently. However, it requires careful parameter tuning to achieve optimal performance. Our next heuristic method is simulated annealing. It is a heuristic optimization algorithm and it is inspired by the process of annealing in metallurgy. When metals are heated to high temperatures and then gradually cooled, their atoms rearrange to minimize energy and form a stable crystal structure. In solving the traveling salesman problem, the algorithm starts with an initial solution, which could be a random tour. It then iteratively explores neighboring solutions by making small changes, such as swapping two cities in the tour. The goal is to find a solution with a lower cost of tour length. If a new solution is better, it is always accepted. However, if it is worse, it may still be accepted with the probability calculated using the formula P is equal to E raised to the power minus delta E by T. Here, delta E is the increase in cost and T is a temperature parameter that starts high and gradually decreases. Early in the process, when T is high, the algorithm is more likely to accept worse solutions. This helps it escape local optima and explore a broader range of possibilities. As the temperature decreases, the algorithm becomes more selective, refining the best solutions. Simulated annealing is simple, robust, and effective for large traveling salesman problem instances. But again, its performance depends heavily on the cooling schedule and the way neighboring solutions are generated. Moving on to our next algorithm. The last algorithm that we analyzed was a genetic algorithm. It is inspired by the process of evolution by natural selection. It operates on a population of candidate solutions which evolve over generations to find increasingly better solutions. Each candidate solution, called an individual, is represented as a chromosome, a sequence of cities. The algorithm begins by generating an initial population, often at random, then it repeatedly applies three operations. Selection. Individuals are selected for reproduction based on their fitness, which in traveling salesman problem is inversely proportional to the total length. Fitter individuals are more likely to pass on their characteristics to the next generation. We use methods like roulette wheel selection and tournament selection. Next, the crossover. Pairs of selected individuals are combined to produce offspring. For example, in partially matched crossover, segments of a tour from each parent are swapped to create new solutions. This helps introduce diversity into the population while preserving good traits. And lastly, mutation. To avoid premature convergence, random changes are introduced in the offsprings, such as swapping two cities in the root. This ensures genetic diversity and allows the algorithm to explore new paths of the solution space. This process continues for a set number of generations or until no significant improvement is observed. Over time, the population evolves to include better solutions. Genetic algorithms are particularly powerful for large and complex traveling salesman problem instances because they leverage parallel exploration of the solution space and can adaptively improve over time. We implemented all of the algorithms that we discussed on problem sizes of 4 to 10 and 30 and analyzed the performance on the basis of their optimality, computational time, and scalability. Here are the results. The 4 cross 4 matrix, all algorithms successfully found the optimal solution of 80. This validates the efficiency of exact methods for small problem sizes while confirming the reliability of heuristics. For the 10 cross 10 matrix, exact methods showed optimal solutions, but there was a noticeable increase in their computational time, especially in the branch and bound. Among the heuristics, ant colony optimization matched the optimal solution and demonstrated excellent performance in both quality and time, while simulated annealing came close with a minor deviation, but the genetic algorithm lagged, producing a suboptimal result and required more computational time. This highlights the growing advantage of heuristic methods as problem size increases. For the 30 cross 30 matrix, exact methods became computationally infeasible because of their exponential time complexity. Among the heuristics, ant colony optimization emerged as the most effective one with a reasonable computational time. Simulated annealing also performed well, offering a near optimal solution in the shortest time of all algorithms tested. The genetic algorithm, however, produced suboptimal results with an average tour length of 947. It highlights the limitation for larger instances. These findings underline the scalability and efficiency of the ant colony optimization and simulated annealing for larger problem sizes. In summary, our experiment demonstrated clear trade offs between exact and heuristic methods. While exact methods guarantee optimal solutions for small problems, their computational demands grow exponentially with the matrix size. Heuristics, like the ant colony optimization and simulated annealing, strike a balance between computational time and solution quality. With ant colony optimization consistently outperforming other methods, these findings highlight the importance of selecting the right algorithm based on the problem size and computational constraints. We have explored everything in more detail in our research paper, and this PPT was only for presentation point of view.